Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all in class of elementary number theory by David and Burton. Our discussion is continue on chapter number 8, primitive roots and indices. Alhamdulillah, in last lecture we have completed section 8.1. In today's lecture we are going to start section 8.2. That is primitive roots and primes. This section has a very important property. In last section, we have found primitive roots for different numbers. You have seen that it is not necessary that every composite number has a primitive root. Like n is equal to 8 has a no primitive root. But in this section, we will discuss that the prime number p, every prime number p has a property that it has at least one primitive root. One primitive root. For example, you have seen that when our modulo is prime p and it is equal to 7, then one of the primitive roots is 3. So it is the property of any prime number p that it has must at least one primitive root, and the maximum number of primitive root for any prime p are given by the formula phi of p minus 1, and this formula is not different from the earlier one. For any integer n, either it is prime or composite, the total number of primitive roots are given by the formula phi of n, and where phi is a Euler Totient function that gives the number of all positive integers which are relatively prime to n and less than n. So these two formula are actually same for when n is prime p, because when n is prime p, then in this case phi of n is simply given by phi of p, and phi of p is calculated by p minus 1. So inside the bracket this is equal to p minus 1, so that's why this formula becomes phi of p minus 1. So the total number of primitive roots can be calculated by phi of p minus 1. In case when your p is 7, then total number of primitive roots are phi of 7 minus 1, which is equal to phi of 6. And to calculate phi of 6, we make its prime factorization. The prime factorization of 6 is 2 into 3. Now we can separate phi at each number. This becomes phi of 2 into phi of 3. This is the multiplicative property of phi function. Phi of 2 is again a prime number, so its value is 2 minus 1, and this is equal to 3 minus 1, and which is equal to 2. So in case when your p is 7, then total number of primitive roots are 2. So before going into detail of this section, in this lecture we will discuss the very important theorem that is called the Lagrange Theorem for polynomial congruences. So let us state and prove Lagrange Theorem for polynomial congruences. Lagrange theorem of polynomial for polynomial congruence in number theory have the same concept that you have learned in your calculus or real analysis course. From calculus, if you have any polynomial f of x equal to 0, then the number of solutions or roots for this polynomials depend on its degree. For example, if f of x is equal to second degree polynomial, then the equation x square plus 3x plus 5 equal to 0. Suppose this is my second degree polynomial equation. You know, this equation has two different roots. So similarly, if you have a third degree polynomial, cubic polynomial, then it will have three distinct roots, or we can say that third degree polynomial has at most three roots. It may be all are different, or maybe some of them are same. So the Lagrange polynomial for congruence actually have the same basic concepts as we discussed in calculus. So what is the statement? Statement of Lagrange theorem. Lagrange's theorem for polynomial congruences, or polynomial congruences. It can be stated as let P is prime let P is prime and f of x is equal to an x raised to power n minus 1 an minus 2 x raised to power an minus 1 x raised to power n minus 1 up to so on a1x plus a naught, with the condition that GCD of with the condition that an is not congruent to 0 modulo p is a polynomial of degree n greater than or equal to 1 with integral coefficients then the congruence f of x congruence to 0 modulo prime p has at most here will be n has at most n incongruent solutions modulo p. So this is the statement of Lagrange theorem. This says if p is any prime p, then the polynomial, this is the nth degree polynomial, with a condition that the leading coefficient, that is the coefficient with the highest degree term, is not congruent to 0 modulo p, and all of the coefficients are integer here. Then f of x congruent to 0 has at most an incongruent solution modulo p. Here you can notice that this congruence, when we say an is not congruent to 0, it means that p does not divide an minus 0, and further it means p does not divide an. As p is a prime number and a is an integer, it also means that GCD of p and an is equal to 0. In other words, p and an are all relatively primes. So you can write this statement also instead of this. So to prove the Lagrange theorem, I will use the mathematical induction. In mathematical induction, the first statement we check for n is equal to 1. N is equal to 1 mean we check that the linear congruence has at most one solution. Suppose if we check the statement for n is equal to 2, it means that we have to show that the quadratic congruence has at most two incongruent solution. So proof. To prove the theorem, we will use the mathematical induction. You will write here base step for n is equal to 1. For n is equal to 1. When our n is equal to 1, then this polynomial becomes the linear polynomial, that is f of x is equal to a1x plus a naught. So we have a linear congruence. We have linear congruence given by f of x congruent to 0 modulo p. In this case, our f of x is a linear polynomial, so this becomes a1x plus a naught congruent to 0 modulo p. And this can be written as a1x is congruent to minus a naught modulo p. As it is given in the statement that an is not congruent to 0 modulo p, whose alternate meaning are GCD of p and an is equal to 1. So here, as GCD of a1 and p is equal to 1, because this result holds for every integer, for every coefficient. So particularly this will hold for coefficient of x also. As GCD of a1 and p is equal to 1, so by the result that can be stated as, you will write here, this result I have discussed in my previous lecture in chapter of congruences. If we have a linear congruence ax equal congruent to b modulo some integer n, then this result says that if the GCD of a and n, if GCD of a and n is equal to 1, then this linear congruence has a unique solution always. So you will give the reference of this result. You will write here, we know that from the result that this linear congruence has a unique solution if the GCD of the coefficient of x and modulo n is equal to 1. Then this linear congruence has a unique solution. So applying this result here, this implies one has unique solution. Unique solution. So we can say see that the statement is true for n is equal to 1. When n is equal to 1, we have a linear congruence, and in this case we have proved that this linear congruence has a unique solution by using this result. Next, we suppose that the statement is true for n is equal to k minus 1, and we will consider the theorem for n is equal to k. Okay. Next we suppose that theorem is true theorem is true for n is equal to k minus 1. N is equal to k minus 1 means we have assumed that we are going to assume that any polynomial whose degree is k minus 1 will have always at most k minus 1 primitive incongruent solution, sorry. So, and we consider the theorem for n is equal to k. So here we will discuss the two cases. Case number 1. Case number 1. If f of x congruent to 0 modulo prime p has no solution. When we say this congruence has no solution, it means there are zero solutions and definitely 0 is less than k, where your k represent the degree of the polynomial, which is here greater than equal to 1. So result is true for this case. Result is true for this case. When you say f of x congruent to 0 has a no solution, it means the number of solutions are 0. What we have to prove in Lagrange theorem? In this theorem, we have to prove that if your polynomial f of x has a degree k, then number of incongruent solutions are at most k. At most k means the maximum number of solutions are k. So when you say your congruence f of x congruent to 0 modulo p has a no solution, it means there are number of solutions are 0, and 0 is definitely less than k. K means the number of degree. So if the degree is k, then the number of incongruent solution will be k. So 0 is always less than k for any k greater than 1. So this result hold according to the theorem. Case number 2. In this case, we will suppose that this congruence has at least one solution. Suppose f of x congruence to 0 modulo p has at least one solution. Say it is A. Suppose this is the solution of this linear congruence. Okay, if A is one of the solution of this linear congruence, so when we divide, polynomial f of x by x minus a. This is same as you have learned in your school level or college level algebra. When you divide any second degree, suppose f of x is a second degree polynomial, and x is equal to a is one of the root. Suppose your polynomial is x square minus 4. You know x is equal to 2 is one of its root. So you can divide this polynomial by x minus 2, the linear factor x minus 2. So when we divide f of x by x minus a, then by division algorithm, we can write f of x is equal to x minus a into some quotient qx plus remainder r. Say this is 1, this is 2, sorry. Suppose you can understand this is my polynomial f of x, you divide it by x minus a. It must be that here there will be some quotient qx, and this quotient qx is some polynomial in integral coefficients, and after multiply this we have some remainder r. So we can write by division algorithm, this is my dividend f of x equal to some divisor x minus a into some quotient qx plus remainder r, where you will write where qx is clearly a polynomial of degree. What will be its degree? If f of x is a kth degree polynomial, and when you divide a kth degree polynomial by a linear factor or linear polynomial x minus a, then the quotient qx will be a k minus 1 degree. You can understand this fact from here. If you divide x square minus a square over x minus 2, here it will be x plus 2. So you can see here what is quotient. Quotient is x plus 2, that is a linear polynomial. Similarly, if you divide x cube minus 8, this is the third degree polynomial, by x minus 2, here there will be a some polynomial qx. What will be its degree? Its degree will be second degree, because third degree, when we divide third degree polynomial by a first degree linear factor, it will give us second degree polynomial. Okay, so where qx is clearly a polynomial of degree k minus 1 with integral coefficients, because f of x is itself a integral coefficients polynomial, so qx will also be a integral coefficients polynomial with integral coefficients, and r is a remainder which will always be an integer, and r is an integer. Because here x is equal to a is one of the solution of f of x, so it means x minus a is the factor of f of x, and by the definition of a factor is an expression that divides a polynomial completely with zero remainder. Next we show that this remainder r in expression 2 is equal to 0 under modulo p. This is our target. Next we show that r is 0. You will write as x equal to a is a solution of f of x congruent to 0 modulo p. This implies this will satisfy this congruence. We have f of a congruent to 0 modulo p. If we substitute x is equal to a here, substituting x is equal to a into and using 3 we have, when you put x is equal to a, there this will become a minus a into q of a plus remainder r, and this side is equal to f of a, which is congruent to 0 modulo p. Modulo p. A minus a, this is 0. 0 into qa, this is also 0. And finally we have r congruent to 0 modulo p. This implies your f of x is congruent to x minus a into q of x. Just a minute, after Azan we have discussed the remaining proof. Okay, next we want an expression which just involve the polynomial q of x and independent from f of x and this factor x minus a. For this we suppose let x is equal to b is another incongruent solution of f of x congruent to 0 modulo p other than x is equal to a. Other than x is equal to a. So if x is equal to b is an other solution because this polynomial has at least we have stated that this polynomial has at least one solution. So we can say that there exists another solution x is equal to b for this congruence. So if x is equal to b is its solution, then clearly it will satisfy this congruence, and we can write f of b congruent to 0 modulo p. Say this is my congruence 4. Now substitute x is equal to b in 4. We have this become f of b congruent to b minus a, and this is q of b. As f of b is congruent to 0, so this becomes 0 congruent to b minus a into q of b modulo b here modulo p. As a and b are two different solutions, so they cannot be equal, as a is not congruent to b modulo p, because we have stated as x is equal to b is an other incongruent solution other than x is equal to a. It means this implies b minus a cannot be congruent to 0 modulo p. This implies if this factor b minus a is not congruent to 0, it means the other factor q of b is congruent to 0 modulo p. This is the same concept that we used in algebra. For example, when you say the product of two integers x and y is equal to 0, then it is possible that both of them are 0 or at least one of them will be 0. So either x is equal to 0 or y is equal to 0. The same concept we can use here. When you say b minus a is not congruent to 0, suppose we say b minus a is not equal to 0. Then what is the possibility for equality to 0? This number q of b is congruent to 0 modulo p. What does this show? This shows that any solution of f of x equal congruent to 0 is also the solution of q of x, because x is equal to b, the solution of f of x, so we have f of b congruent to 0. Similarly, we have proved that q of b is also congruent to 0. It means x is equal to b is also a congruent solution of q of x. This means any solution of f of x congruent to 0 modulo p is also a solution of q of x congruent to 0 modulo p. Now, what was the degree of q of x? The degree of q of x is k minus 1, as q of x is a k minus 1 degree polynomial, and we have assumed that in the inductive step any k minus 1 degree polynomial has at most k minus 1 incongruent solution. This was our assumption. So by our assumption q of x has at most k minus 1 incongruent solutions. This implies f of x congruent to 0 modulo p has at most k incongruent solution. How? This is simple because we have proved that f of x is congruent to x minus a into q of x modulo p. When you say q of x, this is a k minus 1 degree polynomial, so it has k minus 1 incongruent solution. Clearly x minus a is a linear polynomial, so it must has only one solution. So the total number of solutions are equal to k. That we have to prove. So this completes the proof of Lagrange theorem for polynomial congruence. I hope you have a clear understanding about the statement and proof of Lagrange theorem and section 8.2, that is the primitive root for primes. Inshallah, in the next lecture, we will discuss a very important corollary that is related to this Lagrange theorem and frequently asked in your final exams. So, see you in the next lecture. Take care. Allah Hafiz.